In problem 1 on the practice final, we need to find the limit of this function as x approaches 3. You're asked to do it with a graphing calculator. Here you have to be careful. I'm also going to show you how to do this analytically, but to start off with, let's put this in your calculator. You have to do this accurately, which means you need to put parentheses around the x squared minus 9 and then parentheses around the denominator. And if you put this on your calculator, you can see that the function is not defined in x equals 3. Basically, you're seeing 0 over 0. So the question is, does the function as x approaches 3 actually have a limit? And if you put this in your calculator, you'll see a graph that looks something like this. And as x approaches 3 from the right or the left, there's a hole in it at x equals 3, but you'll see that the limit is equal to 8. Now, to do this analytically, we want to use a strategy that we've illustrated in class before, in which we multiply the denominator and the numerator by the same function. So here we're going to multiply the top and the bottom by the square root of x squared plus 7 plus 4. We're going to do the same thing to the top. And if we do that, we get the limit as x approaches 3, x squared minus 9, the square root of x squared plus 7 plus 4, the denominator becomes x squared plus 7 minus 16. And if you simplify this, you get x squared minus 9, the square root of x squared plus 7 plus 4. The denominator becomes x squared minus 9. Notice we cancel out x squared minus 9, and we get that this limit is equal to the square root of 9 plus 7 plus 4 is equal to 8. So the answer is 8. Problem 2, we want to find the equation for the tangent to the curve at the given point. And the function we're looking at is x minus the square root of x. So the first thing you need to do is figure out what the derivative of the function is. The derivative of the function is equal to 1 minus 1 over 2 times the square root of x. And so we need to calculate the slope of the tangent line at that point. That would be f prime at x equal 1. And we get 1 minus 1 over 2 times the square root of 1, which is equal to 1/2. So that is the slope of the tangent line. So we then now simply write down the equation for a straight line as y minus y1 equal m times x minus x1. So we get y minus y1, which is 0, equals m, which is 1/2, times x minus x1, which is 1. And so we get y is equal to x over 2 minus 1/2, which is equal to answer B. Problem 3, we want to find the second derivative of the function. And quite often, before you go using a lot of techniques to calculate this function, you need to look at it and see if there's a way to simplify it, and then take the derivative. So here you would simplify before taking the derivative. So let's do that. Let's write this as y equal x cubed minus 8x squared minus 20x divided by x cubed, which is equal to 1 minus x 8x to the minus 1 minus 20x to the minus 2. Now you can very easily take the derivative as equal to 8x to the minus 2 plus 40x to the minus 3, and then take the second derivative, which is minus 16x to the minus 3 minus 120x to the minus 4, which can be written with positive exponents as minus 16 over x cubed minus 120 over x fourth, and that's answer B. Problem 4, we want to take the derivative of the function. And it looks like we're going to need to use the quotient rule. In fact, we have two quotients. So the first derivative using the quotient rule, remember that would be the denominator times the derivative of the numerator, which would be the derivative of the numerator would be cosine of x minus the numerator, which is sine of x, times the derivative of the denominator, which is 7, divided by the denominator squared, which is 7x quantity squared, plus using the quotient rule again, it would be sine of x times the derivative of the numerator, which is 7, minus 7x times the derivative of the denominator, which is cosine of x, divided by the denominator squared, which is sine squared of x. Simplifying this, we get x times 7 cosine of x minus sine of x divided by 49x squared. Notice this is going to simplify to being 7x squared. And the second expression is 7 times sine of x minus 7x cosine of x divided by sine squared of x, and looks like that is answer B. Problem 5, we have a particle that is moving on the curve defined by y equal 5 sine square of x. And it's moving with a constraint that the dy dt is always equal to 5, and we want to find the instantaneous rate of change of x with respect to t when x is equal to pi over 4. So we want to find the derivative of x with respect to t, which means we need to take the derivative of y first with respect to t, which is equal to 10 sine of x cosine of x. Remember the chain rule, times dx dt. Chain rule again. So we had to first of all take dy dx and multiply times dx dt to get dy dt. So we have that dy dt is always equal to 5. That's equal to 10 sine. We want to calculate dx dt when x is equal to pi over 4. So we have sine of pi over 4 cosine of pi over 4 times dx dt. So we have 5 is equal to 10 sine of pi over 4, which is the square root of 2 over 2, cosine of pi over 4 is the square root of 2 over 2, times dx dt. And it looks like we have 5 equal to 5 dx dt. So we get a very simple answer that dx dt is equal to 1. So it's answer A. Problem 6, we want to find extreme values of the function and where they occur. If you're looking for a relative minimum or maximum, we want to take the first derivative of the function and see where it's equal to 0, and then test the second derivative. Well, the first derivative is equal to 3x squared minus 12. This equals 0 at x squared equals 4, which means that x is equal to plus 2 and x equal minus 2. Now, in order to determine whether these are a relative max or a min, or maybe not even a relative max or a min, which means the second derivative might be 0. So we're going to take the second derivative to see what its sign is. The second derivative is equal to 6x. So the second derivative at x equal minus 2 is equal to minus 12, which is less than 0. So it's concave down, which means it looks like this. That means it's a relative max. If we check the second derivative at x equal plus 2, we get 12. It's more than 0, means it's concave up, which means a relative min. So looks like the answer is a relative max at minus 2, relative min at plus 2, and of course the values of the function at minus 2 are plus 18 and minus 14 respectively if you plug that in. Problem 7, we're trying to find the dimensions of a metal tank that will yield the minimum surface area. The constraint is that the rectangular tank must have a volume of 46.5 cubic feet. Now, if you look at this tank and it says it's a square base tank, so if it's a square base tank, it's going to be X by X, and I'm not a great artist by any means, but you can imagine that the height of this tank would be Y. And so the volume of the tank would be X squared times Y. And it is said that that volume has to be 46.5. Now the surface area of the tank, notice it's open at the top, so we're talking about 5 sides. That would be the left, the right, the back, and the front, and the bottom. So the surface area would be the area of the bottom, which would be X squared, plus 4 times the area of the sides, which would be 4XY. Now, so we want to find the minimum surface area. In other words, find dimensions that will make the surface area the minimum. Well, notice we have 2 variables here, and we need to eliminate one of them. And we do that by looking at the constraint equation, which we can solve for Y as equal to 46.5 over X squared, which we then proceed to substitute in the area equation. So we get area is equal to X squared plus 4X times 46.5 divided by X squared. Taking dA dx, we get 2X plus, first of all, we would write this as 4 times 46.5 over X. And so taking the derivative of the second portion, we would get minus 4 times 46.5 over X squared. And we want to set that equal to 0, which means that 2X cubed minus 4 times 46.5 equals 0, or X cubed is equal to 2 times 46.5, and X is equal to the cube root of 2 times 46.5, which is equal to 4.53. And then substituting for Y equals 46.5 over X squared, we get 46.5 over 4.53 squared, and we get that Y is equal to 2.26. So we round that off to 2.3, and we round this off to 4.5. So we get answer B, which is 4.5 by 4.5 by 2.3 feet. problem 8, we want to take the derivative of the integral, and for this we would use the fundamental theorem of calculus. Here I'd like to review this a little bit. Remember, the fundamental theorem of calculus, which is the first one we learned, was if you have y is equal to integral from 0 to x of some f of t dt, that dy dx is equal to f of t, which means you just substitute the x everywhere you see a t in the function under the integral sign. I want to caution you that if you have y equal the integral from 0 to some g of x, that now y prime or dy dx is equal to f of g of x. In other words, you substitute the top everywhere you see a t, but then you have to multiply by g prime of x. And that's what many of you have forgotten to do on this kind of problem. You got to remember the chain rule. So let's do this. Y prime equal dy dx equals the square root of the tangent of x times d dx of tangent of x. So that's the square root of tangent of x. The derivative of tangent of x is equal to secant squared of x. So that is answer C. Number 9, we want to calculate the general antiderivative. And here again, it's a good thing to simplify an expression before you try to take the antiderivative. It will save you a lot of trouble. We can rewrite this as x to the 3/2 plus x to the 1/2 divided by x squared dx. And now rewriting this equals the integral of x to the minus 1/2 plus x to the minus 3/2 dx, which is equal to x to the 1/2 divided by 1/2 plus x to the minus 1/2 divided by minus 1/2. Recall, this is minus 1/2 plus 1 over minus 1/2 plus 1. This is minus 3/2 plus 1 divided by minus 3/2 plus 1. So the answer is 2 times the square root of x minus 2 over the square root of x plus a constant. Don't forget your constant. And so the answer is answer C. Problem 10, we have a related rate problem. We have a sphere whose volume is increasing at the rate of 9 cubic centimeters per second. We want to find the rate of change of its surface area when its volume is 32 pi over 3. Well, we're looking at surface area and we're looking at volume, so we really need to know formulas for the volume of a sphere. The volume would be 4/3 pi r cubed. The surface area would be 4 pi r squared. Now, we're told that dV dt is equal to 9. Notice we got the volume here, and we can take dv dt would be equal to 4 pi r squared times dr dt using the chain rule. Now, we need to find out what the radius is when the volume is 32 pi over 3. So 32 pi over 3 is equal to the volume is equal to 4/3 pi times r cubed, and we get that r cubed is equal to 8 and r is equal to 2. So now we know what the radius is at this point, and we want to find the rate of change of the surface area. So now that's the last part that we do. dA dt is equal to 8 pi r dr dt. So let's look at what we have. dA dt is what we want. We know that the r is 2. And we need to know what dr dt is. Well, here we have a formula that has dr dt in it. We're given that dv dt is equal to 9 equals 4 pi times r squared, which would be 4. R is equal to 2, recall. So dr dt can be determined from this equation. So dr dt is equal to 9 divided by 16 pi. So now we're able to calculate everything. Notice you're having to put a lot of information together. dA dt would be equal to 8 pi times 2 times dr dt, which is 9 over 16 pi. Simplifying this, you get that dA dt is equal to 9 square centimeters per second. Problem 11, we have another related rate problem. We have an airplane approaching an airport. Let's say the airport is right here, and it's approaching the airport from the north at, let's say the distance from the airport is equal to y, and we're given that dy dt is equal to minus 122 kilometers per hour. We have another airplane approaching from the east. Let's call that distance from the airport as x, and we're given that dx dt is equal to minus 188. And the question is, when the southbound plane is 35 kilometers away from the airport and the westbound plane is 17 miles away from the airport, what is the rate of change of the distance between the two planes? Well, we'll call the distance between the two planes as z. So we know that z squared is equal to x squared plus y squared. Taking the derivative on both sides of this equation with respect to t and using the chain rule, we get 2z dz dt equal 2x dx dt plus 2y dy dt. I'm going to divide everything by 2 and solve for dz dt. dz dt is equal to x dx dt plus y dy dt divided by z. Substituting in for x, we get 17 dx dt is minus 188, y is 35, and dy dt is minus 122, and z would be the square root of 17 squared plus 35 squared, Pythagorean theorem. Plugging all that in, you get minus 191.88. Rounding to the nearest whole kilometer per hour, we get minus 192 kilometers per hour. And that is answer C. Problem 12 is another related rate problem. And we have a 6-foot-tall man, and he walks away from a lamppost that is 23 feet high. So he's walking away from a lamppost, and he's 6 feet high. And we want to find the distance, the rate at which the length of his shadow is changing. Now, if this is a lamppost, his shadow would be this dimension. And we're told we want to find out how fast dy dt is changing when he is 70 feet from the lamppost. Okay? So let's look at this. We need to get a relationship between y and x, which is the distance of the man from the lamppost. Now notice we have similar triangles. We know that 23 divided by x plus y is equal to 6 over y. Notice you can't just plug in 70 because this is a dynamic situation and we're only looking at what the value of the derivative of the shadow is when he's 70 feet away from the lamppost. So we have to put the distance from the lamppost as x plus y. So 23 divided by x plus y is equal to 6 over y. Cross multiplying, we get that 6x plus 6y equal 23y. And we get a very simple relationship that 6x equals 17y. So y is equal to 6/17 x. So we get that dy dt is equal to 6/17 dx dt. So dx dt, we're told, is 3 feet per second. So dy dt is equal to 6/17 times dx dt, which is 3, which is 18/17 feet per second, which is answer C. Problem 13, we want to find the area of the shaded region, which really means we want to calculate the integral from 0 to pi over 4 of the top curve, which is secant squared of x, minus the bottom curve, which is cosine of x dx. So we need to take the antiderivative of secant squared of x, which is tangent of x, and the antiderivative of cosine of minus cosine of x is minus sine of x, and evaluate that between 0 and pi over 4. So we get tangent of pi over 4 minus sine of pi over 4 minus tangent of 0, which by the way is 0, minus sine of 0, which is 0. So we get the simple answer is 1 minus the square root of 2 over 2, which is answer A. Problem 14, we have a definite integral, and we want to use substitution to, first of all, calculate the antiderivative and then use the substitution formula. So we need to come up with a reasonable substitution. Notice the derivative of tangent is like secant squared. So it seems like using u equals tangent of 2x would be a reasonable substitution. So du is equal to 2 secant squared of 2x dx. Notice that we have to use the chain rule when we take the derivative tangent of 2x. So it's secant squared 2x times the derivative of 2x, which is 2. That means that secant squared of 2x dx is equal to du over 2. Now when we make the substitution, since it's a definite integral, the u upper value is going to be tangent of 2 times pi over 8, which is tangent of pi over 4, which is 1. U lower is going to be tangent of 2 times 0 is equal to 0. So the entire integral becomes the integral from 0 to 1 of 1 plus e to the u. Remember, u is equal to tangent of 2x. So the u goes here. And secant squared of 2x dx was equal to du over 2. So now this is what we have to take the integral of, and this is u over 2 plus e to the u over 2, evaluated between 0 and 1, and this is 1/2 plus e to the 1, which is e over 2, minus 0 minus e to the 0 over 2, which is equal to e over 2, which is answer C. Number 15, we need to evaluate the integral, and it's an indefinite integral, so we need to remember to add the constant. Here again, strategy to solve this is to use an appropriate substitution. And here I would use u equal 7x squared plus 3, meaning that du is equal to 14x dx. So x dx is equal to du over 14. So doing the substitution, we get x dx, which is du over 14. And then with the substitution, 1 over u to the 5th divided by 14. Now, this is equal to the integral of u to the minus 5 over 14 du equal minus u to the minus 4 over 4 times 14 plus a constant. And so we get, after resubstituting the value of u, we get minus 150 over 56, 7x squared plus 3 to the minus 4 plus a constant, and that is answer D. Problem 16, we want to take the derivative. Here we have a product. You could multiply this out and then take the derivative. It also looks like it might be just as easy to do this by using the product rule. Using the product rule, we get that the derivative is equal to the first times the derivative of the second, which is 14 x to the 6, plus the second, which is 2x to the 7th minus 8, times the derivative of the first, which is 15x squared. After you multiply all this out, you get 70x to the 9th plus 42x to the 6th plus 30x to the 9th minus 120 x squared. Combining all these terms, and you get 100x to the 9th plus 42x to the 6th minus 120x squared, and that is answer B. Find the derivative of the function. Number 17. Here, There's just no way around this. Generally, you need to use the quotient rule. So g prime of x would be equal to the denominator times the derivative of the top, which is 2x, minus the numerator, the top, which is x squared plus 5, times the derivative of the denominator, which is 2x plus 6, divided by the denominator squared. Multiplying this out, we get 2x cubed plus 12x squared minus 2x cubed minus 6x squared minus 10x minus 30, all divided by, I'm going to factor an x out of this. So I would get x squared times x plus 6 squared, and notice the x cubes cancel. I get 6x squared minus 10x minus 30 all over x squared times x plus 6 squared, and that is answer B. Problem 18. We want to take the derivative of this function, and you can see right away we need to use a chain rule. This is like the inner function u, so the derivative would be 5 u to the 4th times du dx. And if we do du dx, we're going to have to use the quotient rule again. So h prime of x is going to equal to 5 cosine of x over 1 plus sine of x to the 4th power times d dx of cosine of x over 1 plus sine of x. So here we got the chain rule mixed in with the quotient rule. You got to keep all this straight. And so we get 1 plus sine of x, the denominator, times derivative of the numerator, which is minus sine of x, minus the denominator, or minus the numerator, which is minus cosine of x, times the derivative of the denominator, which is cosine of x, and divided by the denominator squared, which is 1 plus sine of x, quantity squared. Now, this is 5 times cosine of x over 1 plus sine of x, all to the 4th power. After we multiply this out, we're going to get minus sine of x minus sine square x minus cosine squared of x, divided by 1 plus sine of x, quantity squared. Notice that sine squared, that this term here is going to be minus 1 plus sine square x plus cosine squared of x. And you recall from trig that sine squared, this is minus sine of x, that comes from here, plus sine squared plus cosine square x, which is 1. So this becomes minus 5 cosine of x over 1 plus sine x to the fourth times 1 plus sine of x divided by 1 plus sine of x squared. So this cancels out one of these, and we get minus 5 cosine of x to the fourth power times 1 plus, divided by 1 plus sine of x to the fifth power. And that is answer D. Here you had to use a well-known identity, sine square x plus cosine square x equal 1. Problem 19, we want to use implicit differentiation to find dy dx. So looking at xy plus x plus y equal x squared y squared, we want to take d dx of both sides. To take d dx of xy, that's a product, so we use a product rule. So we get x times dy dx plus y times d dx of x, which is 1. d dx of x here is 1. d dx of y is just dy dx. Taking d dx of x squared y squared, we have to use the product rule, so we get x squared times d dx of y squared, which would be 2y dy dx plus y squared times d dx of x squared, which is 2x. So multiplying all this out, I get x dy dx plus y plus 1 plus dy dx plus 2x, excuse me, that's an equal sign now, equals 2x squared y dy dx plus 2x y squared. Now we need to collect all the terms with dy dx and put them on one side of the equation, and we get dy dx times x plus 1 minus 2x squared y, comes from there, equals 2xy squared minus y minus 1, which comes from here. And so we finally solve for dy dx is equal to 2x squared, to 2x y squared minus y minus 1 divided by minus 2x squared y plus x plus 1. And that is answer A. problem 20, we're given a figure that shows the velocity of a body moving along a coordinate line as a function of time. And we want to answer the question, when is the body's acceleration equal to 0? Well, the acceleration is equal to, first of all, the second derivative of the position, which is equal to the first derivative of the velocity. So it equals 0 when v prime equals 0. Well, we're given a graph of v, so we need to look at where is v prime equal to 0. Well, that would be here and here. And so we notice that there's a flat function there, or 0 derivative over the integral, or over the interval 2 to 3 and over the interval 5 to 6. So the answer would be D, t between 2 and 3 and t between 5 and 6.